Hi, I'm here to present a mechanism for intelligence. A mechanism that will enable us to find initial meaning from nothing, build that into increasingly bigger ideas and concepts, and potentially recreate the human knowledge that we have today and then push further beyond. So this will also be a potential mechanism for creating true AI. This will be divided into 5 parts. In this intro, I'll define exactly what I mean by intelligence and discuss some of the challenges in trying to achieve it. In part 1, we'll discuss how things get started. We'll discuss how to find initial direction from nothing through a method that I'll call exploring and checkpointing. In addition, we'll also discuss some related work in the field of reinforcement learning. Reinforcement learning is also interested in the type of general problem solving we're tackling here, but it has a key Markov restriction holding it back. We'll discuss this restriction and explain how we overcome it here. In part 2, we'll discuss how to add increasing sophistication on top of what we built in part 1 through methods of abstraction and generalization. We'll see how to form concepts, add structure, and most importantly, build algorithms. Algorithms are able to utilize the full power of Turing machines, which our human minds are potentially one of, and will be necessary for creating the most powerful ideas. In part 3, we'll discuss some details of supervised learning, which is widely used throughout parts 1 and 2. Existing methods of supervised learning, from statistical techniques to neural networks, are all limited in the computational model, so have significant weaknesses. Instead, I'll show a Turing-complete method of learning, dynamic supervised learning, which is a method that can grow its size, change its structure, and alter its execution according to the details of the problem. Finally, as wrap-up, we'll touch on some additional complexities that are skipped in the main parts of this presentation, discuss some aspects of intelligence more specific to humans, and we'll take a quick look ahead into the future to touch on some of the potential implications of true AI. So let's get started, and I'll begin by informally defining what I mean by intelligence. So by intelligence, I loosely mean the ability to create a plan for achieving a goal. We'll assume the goal here is either given to us or something we intrinsically want. For example, a simple goal here could be easing our hunger when we're feeling hungry. And we'll be given some tools to help us achieve this goal, which, for example, for humans, include our muscles that we can use to move us closer to our goal, and our senses, which can potentially help us decide how we want to fire our muscles. So then, what exactly is a plan? Well, it might include an overall strategy, so a rough outline of steps we plan to perform in general. So, for example, for easing our hunger, a simple strategy could perhaps be to just look for food in the fridge and eat it. Or the strategy can be more complex, involving cooking skills, modern technology, and preparation, execution, polish, and more. The plan might also include tactical adjustments, so knowing what details to pay attention to and how to adjust when different scenarios occur. For example, in cooking, knowing what to do when we notice that certain ingredients or certain equipment is missing. Okay, then generally speaking, how can plans be created and how can we have confidence they'll work? So it is the case that if a goal is completely new and we have no existing knowledge, then we can't create an effective plan and can really only randomly guess at what to do. But as a goal is tackled again and again, we can begin building up knowledge on what works and what doesn't, and use that to construct our plan. And even though every time we tackle a goal, it will be in a new unique time and place, there should still be similarities and constants between attempts at a goal, and those are what we can look for and rely on in our plans. So now, formally, in the following, I'll be defining intelligence in the context of problem solving. So some of this will share similarities with other definitions previously used in AI. So in the following, we'll be focused on solving a single given problem. The single problem, however, can be quite complex. For example, if the given problem was to ease our hunger, this could ultimately involve mastering modern technology and developing culinary skills. A single problem also actually represents infinitely many specific problem instances. For example, each time we get hungry, it will be a new separate instance of the problem of easing our hunger that we have to solve. With each instance, the underlying world changes. So in other words, the details, variables of the problem change. But hopefully, there will be similarities across instances, and those are what we can look for and use to solve a problem. For example, even though each time we cook, the precise ingredients we'll have always differ, the same general techniques of heating, seasoning, etc. consistently apply. To solve a problem, we will interact with it using actions and observations. These will both be given to us as part of the problem, though initially we might not exactly know what they do. Actions generally have some effect on the underlying world, though the effect can be subtle and indirect. For example, for humans, an action will be firing one of our muscles with some chosen amount of strength. Observations are data we receive about the underlying world, so input signals of various intensities, which may help us decide what actions to perform. But like with actions, they may be difficult to interpret and use directly. For humans, we receive observations, for example, through our eyes, which is data on the amount of light in our surroundings, and for example, through our touch, which is data on the amount of pressure against our skin. For each instance, we will interact with it for some duration. So in other words, we'll perform some sequence of actions on it. Then, we'll choose to stop and receive one final score telling us how we did for that instance. For example, for easing our hunger, our sense of hunger will essentially score us on how full we are at the end. Here, we'll say that the score is given to us by an oracle that is included as part of the problem. An oracle will always know the score regardless of the problem instance and what actions were performed. However, it won't tell us how the score is generated, only what the final value is. So for example, our sense of hunger is an oracle given to us as part of our bodies. We might not understand how exactly hunger works, but we'll assume that it will always be able to give us accurate feelings. A solution then is some method of using actions and observations to achieve a high average score across all instances of the problem. It might include an overall action sequence we hope to perform in general, but also a plan for what observations to pay attention to when, and how to accordingly adjust our action sequence. Finally, intelligence is the ability to build good solutions. The higher scoring, more robust, more nuanced the solutions we can build, the more intelligent we are. In particular, we know that humans can build solutions with, among other things, a particular mathematical property. Humans can build solutions that take the form of algorithms, which are able to utilize the full power of Turing machines, such as potentially human minds, to be particularly compact and scalable. It's likely that in order to build up knowledge and innovate ideas like humans, it will be necessary to, like humans, build solutions in a Turing-complete way. And in the following parts, we'll see how this can potentially be done. We'll see how to build solutions in a Turing-complete way, and more generally, see how to build good solutions overall. Before ending this intro though, to tease at the steps ahead, let's discuss some of the challenges that need to be overcome to achieve intelligence. First, the starting point can be extremely limited. As previously mentioned, we often start with a lack of understanding of the problem, including for its actions, observations, and score. For example, for humans, for our muscles, it's difficult initially to trace how firing any specific muscle can impact an overall goal. For our senses, the useful stimuli are initially indistinguishable from the noise, and for a goal like easing our hunger, we may not initially know that our sense of hunger is tied to food. We may not even know what the concept of food is. In addition, there's often both an overwhelming amount of noise to sift through, as well as an overwhelming number of possibilities to think about. For example, for humans, we have a large number of senses, each of which is constantly sending us signals. Some of it could be useful stimuli, but a lot of it is useless noise that we have to figure out how to distinguish and ignore. And solving a problem often requires combinations of actions. So in humans, many muscles firing in coordination in sequence, and there are infinitely many combinations of infinitely different lengths. On top of this, to handle variation in a problem, good solutions often need to be complex combinations of combinations, and there are infinitely more of those. All of this adds up to an overwhelming number of possibilities we might have to consider and try when solving a problem. The other big challenge is that what we're looking to achieve is often very ambitious. We're often looking for solutions that are extremely large. Even something like moving food into your mouth and chewing requires uncountably many muscle movements and processing uncountably many stimuli. And there are much bigger problems with significantly more moving parts and requiring significantly longer periods of time to solve. And it's not just that the solutions need to be large, they also need to handle significant variation. There are countless situations we can, for example, find ourselves hungry in, and with the world constantly changing, there will continually be new situations we'll be hungry in as well that we'll need to be able to solve. And beyond simply being large, we're also often looking for a certain sense of sophistication. As previously mentioned, humans can build solutions in the form of algorithms. What exactly does that look like? and how it can be achieved. And besides that, there are many other things we often associate with intelligence. Theories, concepts, methods. What are those? How do they help, and how are they formed? And so, this is the end of the introduction. In the following parts, we'll see how these challenges can be overcome and see how we can build a mechanism for intelligence.